Today we'll be doing 13.1 experimental and theoretical probability. So this unit is on probability. So I don't know if you've had exposure to probability before or like doing basic probability. Basically, probability is just the likelihood or the measure of the likelihood that an event will happen. Yeah, if you guys could be quiet, that'd be great. Okay. So you'll need to be familiar with some vocabulary. One of those is sample space. And this is just all possible outcomes we're considering. Okay, and I'll give an illustration of all these right after we write down these definitions, but it's good because a lot of these questions on the test and on homework and etc. will use terms like sample space or outcome or event, and you'll want to know what they mean so you know what they're asking. All right, an outcome is a possible result. Not yet, no. Possible results in the sample space. So you have the sample space, that's all the possible outcomes that you could have that you're considering. And then an outcome is just one of those possible results that's in there. So single out one. And an event single or multiple outcomes in the sample space. Okay, so if you were to draw it out, it might look something like this. You have...
Could you slow down just a second?
Sure.
I'm still running.
Yeah, can you like move it down a little bit too? Like all the way, yeah, right there.
Or pass the banana, that'd be great, yeah. All right, so you can see that if you kind of draw it out, just kind of get a sense, you'll have a sample space, which is all the possible outcomes. You'll have an event, which is this smaller rectangle, which is a portion of the sample space, so it's a portion of all the possible outcomes. And then you'll have a single point or just one outcome that you're considering, okay? Now, probability isn't going to work. I mean, there are some formulas we're going to learn, but in general, it's about thinking and reasoning through mostly kind of word problems, which some people really like, some people really don't like. So we'll have to pay special attention to the wording, pay special attention to what's being described and the events being described. But there are two kinds of probability that we can work with. So the first, as the title suggests, is theoretical probability. And that just means calculating the probability of an event prior or before any, prior to or before any experimentation. There should be an in there, sorry. Oh, I ran out of room. All right, so with theoretical probability, it's just about mathematical probability. It's just about determining, okay, you're going to roll a die or a dice, six-sided. What's the probability that I roll a 2? Independent of like actually doing it and trying to figure out how many times out of 10 would I actually roll that.
1 out of 10.
1 out of 6, sure.
You said 1.
If you roll once, but if it over 10,
Dice or
six-sided dice, yeah.
6?
Okay. Now we calculate the probability of an event, and you write the probability of an event like this: P parentheses events. So P stands for probability of an event. This could be the number of favorable outcomes over the number of possible outcomes. So for instance, we can find the probability of rolling a 2 on a six-sided dice. So in the case of a single roll of a six-sided die or dice, and we just want to figure out, okay, what's just the base probability, the mathematical probability, the theoretical probability of rolling just a 2? The way to think of it is to say, okay, my sample space, this large, all the possible outcomes that I have are just 6, right? 1, 2, 3, 4, 5, 6. Those are all the possible outcomes I have on a single roll. And I'm looking for one favorable outcome. That's rolling a 2. So probability of a 2. So the number of favorable outcomes, we only have one favorable outcome, just rolling one number, 2. Over the number of possible outcomes, and on a six-sided dice, there are 6 possible outcomes. So we have 1 over 6. Okay, so you see that our probability is expressed in terms of a fraction, We could also represent this as a decimal. So we could say this is 0.1667. Or we could express it as a percent. So it could be 16.667%. So, what's that?
Do we need the decimal and percent?
That's a good question. I would know it's interchangeable. So it might write that the probability is, it might be a problem where like the probability is 15% of something.
So how would we know it's 16%?
Well, to get from 1/6 to 16%, that's what you're asking. So to convert to decimal, from fraction to decimal, in the case of 1/6, you would plug into your calculator. But if it was 2/4, just be 1/2, right? So let's say it was 2/4. We know it's the same thing as 1/2. And you might know that it can be expressed as a decimal 0.5. Okay, then to convert it to a percent, you're converting this into a whole number, and you move the decimal over twice. And then that will give you 50%. So likewise, if you wanted to go from percent to decimal, you would take, if it was, let's say we're going to 16.667% to decimal, I would just move this decimal over twice to the left. And then you have your decimal evaluation of a percent. All right, but mostly you'll be dealing with the fractions, but you should know that it could be expressed as a decimal, it could be expressed as percent. So, also notice that our probability is a fraction that's less than 1. Your probability is always going to be between 0 and 1. So if you ever do a problem and you end up with, the probability of this is, 1.8, you've done something wrong. So probability, let's see, I'll do it on this page. Probability always between 0 and 1. You could have a probability of 0, right? So I could say, what's the probability of my rolling a 7 on a 6-sided dice? It would be 0 because there's no 7 there. There's no 7 in my total amount of outcomes. So my probability can equal 0. So for example, rolling a 7 on a 6-sided dice. And my probability can equal 1, or it could just be absolutely certain. So 0 is not certain, will never happen. 1 is definitely certain. And for example, I could say rolling any number between 1 and 6 on a 6-sided dice. Okay, so another way to think about it is that your probability, or the number of favorable outcomes, the number of outcomes you want. So like when we said, what's the probability of rolling a 2 on a 6-sided dice? Our favorable outcome was 2, right? One of those numbers. If I said, well, my favorable outcome is rolling a 7 on a 6-sided die, well, there are no 7s. There are 0 7s on a 6-sided die. And there are 6 options, so that's just going to be 0. If I said I'm going to roll any number between 1 and 6, well, numbers 1, 2, 3, 4, 5, 6 are already on the dice. So I have 6 favorable outcomes over 6 possible outcomes. My probability is going to be 1. I'm definitely going to roll some number between 1 and 6 on that dice. So that means that the number of favorable outcomes, the number of outcomes you want, rolling a 2, rolling even numbers, rolling odd numbers, rolling a 2 and a 5, or any combination of that when it comes to dice at least, it's not going to exhaust, or it's not going to be larger than the number of possible outcomes. So that's why rolling a 7 on a 6-sided dice is just probability 0. It just won't happen. Yeah, exactly. That's why it's 0. Probability 0. Okay. So experimental probability is our other kind of key concept here. An experimental probability measures the likelihood, or how probable it is, that an event will occur based on the actual results of an experiment. So when it came to theoretical probability, we were just measuring what the likelihood of a certain outcome is just based upon numbers, right? Based upon how many possible outcomes there are and how many favorite outcomes we had. Here we're actually be going with experimentation, so actually doing something multiple times, seeing what the outcome is, and then figuring out what our probability is based upon that sample set. So one way to express that, it's very similar to how we expressed theoretical probability, is to say the probability of some event is equivalent to the number of times our favorable outcome occurs divided by the number of times what's that? Okay. Sorry, that's might be a little crammed there on the side. So that's the number of times favorable outcome occurs divided by the number of times the experiment is done. All right, so let's try one out here. So these ones are usually a bit more than just rolling a die. So let's say a basketball player made 20 threes of his last 34 shots past the three-point line. All right, so there are some events that's happened. This basketball player has made 23s of his last 34 shots past the three-point line. So here we have experimental probability because we have a basketball player and we have a favorable outcome. He's making 23s, and it's over the number of times that the experiment is done. So what's the experiment? Well, just shooting when you're past the three-point line. That's our experiment in this case. So our first question. What is the probability the player makes a shot? or makes a 3-pointer, let's say. All right, so based upon the numbers we have, the basketball player made 23s of his last 34 shots past the 3-point line. What's the probability of his making a shot on the 3-pointer? What do you guys think? Can you not read it, or? Okay. So in order to figure out what the probability is, we're going to look at the number of times our favorable outcome occurs. What's our favorable outcome here? Well, making a 3-pointer, right? Actually making one. And the number of times the experiment is done. So the experiment here is just shooting, right? Whether or not you make it or miss. What's that?
20 out of 34.
Right, so it's going to be 20 over 34. So our probability is 20 over 34. Because it's the number of times he makes the shot, which is our favorable outcome, over the number of times that he tries to make a shot. And so this is going to be his kind of probability of success, right? Based upon this, it's going to be roughly this probability that he makes another 3-pointer. It's going to, so we'd be able to make this into 10, or we'd be able to reduce this to 10 over 17, and we take out a 2. So you can reduce it if you want. So this means that for every 17 shots past the 3-point line that he makes, he'll make somewhere around 10. So pretty good. That's how you would read that. Yes?
Do you have to reduce it if it's
You don't have to, but it might make it easier sometimes. So, depends. Okay. Now part B. I'm going to do this on the other page. Has everybody written this first part down? No? Okay. There you go. Sure. Okay. Also, guys, remember that when you're facing a problem like this, when you set it up, let's say you made a mistake and you said, okay, it's 34 over 20. That's the probability.
That's not possible.
Right, it's not possible because it to be greater than 1. And our probability has to be less than 1. So it always means that there's got has to be some smaller number over a larger number. So in this problem, we can't, or any of these problems, we can't have something larger than 1. So we can't have a top-heavy fraction. Yeah.
That that event will occur. What's after that part?
This one?
No. Above.
Event will occur
And then
based on
based on the
the actual results of an experiment.
I can read it.
Yeah, no worries. Okay. Okay, B, if the player attempts 100 shots in a season, how many threes is he likely to make? Okay, so we determined earlier that the probability of his making a 3
Is it Steph Curry? Did you make it like 100%?
this is not Steph Curry then. So the probability of his making a 3 is 20 over 34. And remember that this is 20 shots made over 34 shot attempts. So the total number of times that he succeeded is on top. The number of times that he tried is on the bottom. Okay, but now we're wondering, what if he goes on to make 100 shots in that season? What would be his probability, or how many shots would he make? Would he likely make in that season? So we set this up by saying, okay, so our probability is 20 over 34. And then we're going to say this is equal to some value x, where x is the number of shots made, because we don't know, but we're trying to figure that out. How many shots is he going to make in the season? And this is the number on the bottom is the number of shot attempts. So we're going to try to figure out, or we've already given that, so there are 100 shot attempts in that season. All right, so now we just have to solve for x. So we'll cross multiply, get 2,000 equals 34x. Divide 34 over. You plug that into your calculator. And x would be approximately, if you round to the nearest shot, be approximately 59. All right, so in a season where he attempts 100 shots, he's going to make roughly 59. And this makes a lot of sense because 20 divided by 34 is, well, you're not going to see it on there, but it's roughly 0.59. So expressed as a decimal, it's going to be 0.59. And if you're considering this as a percent, if you move the decimal over, it's going to be 59%. And percents are always considered out of 100, so if he attempts 100 shots, he's going to make roughly 59. So this makes sense based upon what our probability is. Okay, I'm going to leave that up there, but I'm going to start writing the next one. So what is the probability of each sum when rolling 2 6-sided dice? I think in the homework problems and stuff, they don't say dice, they say like a 6-sided number cube or something. It's kind of a lame title, so I just use dice, but whatever. All right, so the sums we're going to figure out are 10, 3, and 7. So we're going to figure out when we roll 2 dice that are 6-sided, what's the probability of the numbers that we roll on each dice adding up together to make 10, 3, or 7. Now, one of the ways to figure this out is, or to kind of visually represent this, is to draw a table. So it's going to require a little bit of artwork on our part. Okay, so this is like our sample space. We have, let's call this dice 1. Let's call this dice 2. So we're going to roll both of our dice, and we have in total, because this is a square with 6 units on each side, we have a total of 36 possible outcomes. So for A, the sum of 10, we'll express this over 36. For B, the sum of 3 will be something over 36. And for C, we'll express this over 36. All right, so our whole sample space is, or the number of total possible outcomes is represented by the grid. And we're looking at 3 specific events. What's the probability of rolling numbers such that they add up to 10, 3, and 7? So events are just subsets of sample space, right? So an event is just a number of different outcomes considered together, or just one outcome. So what's the probability of an event rolling a 10? Well, let's say we roll dice 1. We definitely know that 5 plus 5 equals 10. So we roll a 5 dice 1, we roll a 5 on dice 2. So there's 1. And we can also roll a 6 on dice 1 and a 4 on dice 2 and get 10 there. But now you have to consider that you could also do it the opposite way. You could also roll a 6 on dice 2 and a 4 on dice 1. So you have 3 ways when you roll 2 dice to add up to 10. And order matters. So, rolling 6 and 4 add up to 10, sure, but you could roll a 6 on dice 1 and a 4 on dice 2. But you could also roll a 4 on dice 1 and a 6 on dice 2. So you could switch those. So ultimately, the probability of rolling a 10 is going to be 3 out of this 36, right? 3 check marks, 3 little X's, 3 boxes out of the total 36, which are all possible outcomes. So we'll have 3 over 36, and we can reduce that to 1 over 12. So there's the probability of rolling a sum of 10. Now what about 3? Well, if we roll dice 1, we could get a 3, but then we'd roll dice 2, and we couldn't get a 0, so that doesn't work. But we can roll a 2 on dice 1, and a 1 on dice 2. And we can also roll a 1 on dice 1, which is already marked. And we can roll a 2 on dice 2. Yeah. Sorry. Right, so because we can roll a 2 on dice 1, in which case we have to roll a 1 on dice 2. Or we can roll a 2 on dice 2, in which case we have to roll a 1 on dice 1. Does that make sense? Right, the 1 and the 1's not going to equal 2. So, sorry. Oh my gosh. So rolling the 2 on dice 1, in order to get 3, we'd have to roll a 1 here on dice 2. And to roll a 2 here on dice 2, we'd have to roll a 1 here on dice 1. Now we would have to exclude the possibility of rolling a 1 and a 1 as well. So what's going to end up happening is we're going to have to say, okay, there's a 3 out of 36 possibility of my rolling, probability of a 1, of a 2, or 3. Sorry, it's really small. Let me rewrite that. 2 or 3 is 3 out of 36. But we don't want this 2 in here, the probability of a 2. So we're going to figure out what's the probability of a 2 independent of that. That's just 1 over 36, right? And so then we subtract the probability of 2 or 3 minus the probability of 2. And that's going to give us 2 over 36. So then our probability of rolling a 3 is 2 out of 36 or 1 out of 18. Okay, so in this case you would have to consider, well, when I do this chart method, it turns out that I actually have a probability of 3 out of 36, it looks like, but that's not right. So I have to get rid of the probability of rolling a 1 and a 1, which is just 1 over 36. It's just 1 square out of 36. Subtract that, and we'll have 2 out of 36. All right, so number, or C, not number C, but just C. The probability of rolling a sum of 7. So the nice thing about this is that we can roll a 1 on dice 1 and a 6 on dice 2. We can roll a 2 on dice 1 and a 5 on dice 2. We can roll a 3 and a 4, 4 and a 3, 5 and a 2, and a 6 and a 1. So notice here that we have 1, 2, 3, 4, 5, 6 boxes marked as 7, and that exhausts our possible outcomes. So that means that our probability of rolling a 7, close, 6 out of 36. Right, because we've marked 1, 2, 3, 4, 5, 6 potential sums that equal 7. And that's just the same as 1 over 6. Now notice that with these problems, when you set up with a grid like this, especially for dice, they're both 6-sided, the sums are just going to go in these kind of diagonal things. So if you want the sums of 3, you just kind of draw a straight line from 3 to 3. Sums of 4, 4 to 4, 5 to 5, and 6 to 6. So there'd be 6 sums for 7, 5 sums for 6, 4 sums for 5, etc. Which is kind of a fun, I don't know if it's fun, but it's a pattern that comes out.
For me, I did it like an addition to start.
Sure, yeah, that's
I put all my sums in there and counted how many sevens I got.
yeah, that's another way to do it. Okay. Now, when we did B here, when we calculated the probability for 3, we did run into a bit of a snag, right? Because we had to remove the probability of 2. So what we did there is called the complement of an event. Or complement with an E. Would someone mind closing the door, please? That'd be great. Oh, never mind. They're coming in. Oh, okay, yeah. Complements with an E, actually, in this case.
Fierce.
All right, so the complement, that's complement with an E, not like compliment like you're complimenting someone. The complement of an event,
You have a nice watch.
thank you, is just all the possible outcomes in a sample space that are not part of the event. So when we calculated the probability that we would roll a sum of 3, we had to get rid of the probability that we would roll a 2. So we subtracted the probability of a 2 from the probability of rolling a 2 and a 3. So we got rid of the probability of 2. So one of the things you can do is like say, okay, what's the probability of rolling less than 3 on a 6-sided dice? If you roll less than 3, you would just roll a 1 or a 2, so there's 2 options, which is just 1 over 3. Now, what about the probability of not rolling less than 3? So rolling a 3, 4, 5, or 6. That's just going to be 4 out of 6, which is going to be 2/3. Notice then that the probability of an event plus the probability of that event not happening, or non-event, these both add up to be 1. So the probability of my rolling less than 3 is 1/3. The probability of my rolling not less than 3 or greater than 3, or greater than or equal to 3, is 2/3. And 1/3 plus 2/3 is just 1. So it's certain that I'm going to roll either less than 3 or roll greater than 3 in that case. Here we are. Doing math. Bye.
Save yourself, high school self.
Okay. Now, one of the ways to calculate what the probability of non-event is, or the probability of something not happening, is to say 1 minus the probability of that event happening. So okay, so let's say that you roll 6-sided dice. What is the probability your roll is not even? All right, so we're rolling 6-sided dice, and we're wondering what's the probability that our roll is not even, or that our roll is odd. So there are 2 ways for us to figure this out. We'll call it A. One is to figure out what the probability of rolling a 1, a 3, or a 5 is, because those are all of our odd numbers. We have 3 options out of 6 total options, so we'll have 3 over 6, which is 1/2. Another way is saying, okay, I have a probability of rolling even numbers, but I want to figure out what the probability of rolling the odd numbers is. So I can say, well, rolling all the numbers together, all 6 numbers, that's just certain. You're going to roll 1 out of something that's even or odd, probability 1. Minus the probability of rolling the even numbers, which is just 3 out of 6. So that's just 1 minus 1/2, which is 1/2. Okay, so that's one way to do problems like that, by using the complement. And you'll be asked to do that, and you'll be given problems where using the complement is pretty necessary.